Okay, hello. Welcome to my talk, Optimizing Stable Sort in Rust and Mostly Failing. I've seen many talks that talk about great results, success, and this talk I really want to focus on failure, on like making mistakes. Recently I had a project where I wanted to port a promising C sorting implementation to Rust and maybe improve the standard library with it. And along the way, I made many mistakes, and I want to focus on these mistakes and talk about them. A bit about myself: I'm a open source and Rust enthusiast. I love reading books, mostly sci-fi. I enjoy board games, cooking, and many other things. I'm terrible at whistling, I just can't do it. I never learned to drive cars, and I work for MVTec, software GmbH, and we are a Munich-based software company focused on high performance and high quality machine vision. A bit about what I do at my day job. I work on an IDE focused on rapid prototyping machine vision applications. It's called HDevelop. Inside of this, there's a custom programming language with some neat properties, and I also maintain and develop language interfaces. So we have a core library, and there's a C, C++, C#, Python interface for it, and even some older stuff. Yeah, so that's about it. Let's take a quick overview what this talk will contain. At the beginning, there's some basic implementation errors and then later some test methodology mistakes. And at the very end, I want to talk about a subtle issue. I'm not entirely sure I would call it a bug. That's why I named it issue. So let's get started. My very first mistake was to underestimate just how much work this would be, right? I looked at this implementation, I discovered it, and the documentation describes it as a hybrid merge and quicksort named FluxSort, and it's stable, adaptive, branchless, and has exceptional performance. I mean, I looked at the implementation, about 240 lines of code, 0 includes. How hard could it be? Turns out it's more than 1,000 lines of code because the header is including the C files, something I hadn't seen before. There are lines with 7 statements in them, like 7 semicolons, so it's quite dense when you try to look at it. It only works for integers, and what I wanted to create was a sort that's general, right? It works for all types, all user-provided types, and it should not only work for them, it should work well for them. It should not just fall off a performance cliff for user-provided types that don't look like integers. And turns out the implementation is not actually stable as far as I can tell, so there were some functions in there that maybe I imported them wrong, right? But at least as far as I could tell, they produced, they had tests that checked if the sort is stable, if it upholds this property, and they failed this test. So I had to change them. It has, as far as I can tell, right, maybe I did mistakes importing again, but as far as I could tell, there's some function that exhibited undefined behavior. And a very big difference is also there is no panic in C, right? So the implementation, you provided a user-provided comparison function, but this comparison function can only return. In Rust, a user-provided comparison function, it can panic. It returns normally, but it can also panic. And the implementation has to maintain that in any possible scenario where this is-less function is called, a panic happens and the result still needs to be well-defined. The original elements still need to be in your slice, and there should be no kind of unsound behavior because of a panic. So let's look at some basic implementation mistakes. I did some basic mistakes when I ported C logic to Rust logic. There were some off-by-one errors in unsafe Rust code and many other mistakes, but I want to focus on this like incorrect port from C to Rust. So let's take a look at how this user-provided comparison function, how it is defined internally, at least. So this is an internal function of the standard library, and to the outside, the users provide a function that returns an ordering as a result, but internally, this gets translated into a function that only returns a bool, telling you whether or not one element is less than another element. And that's all you have to work with. In contrast, In C, in the standard library QSort, and in FluxSort also, the contract they're going by is this comparison function returns an integer. And we can take a look at the documentation, but in essence, it means you get a negative number. You get a negative number. I guess I'm standing in front of the screen. Okay. You get a negative number if the A is less than B. You get 0 if A is equal to B, and you get 1 or like a positive number if A is more than B. And this is the original I had in C, was checking if A is more than B, right? And initially, this is how I translated it. I asked if A is not less than B, but that's incorrect. The correct version would be to ask if B is less than A. And let's just really walk through it to see why that is. So if we take a look, A is less than B, we don't take this branch. If A is equal to B, we don't take this branch either. But only if A is more than B, we take this branch. And my incorrect version, it was the same for less and more, but when the elements are equal, it also took this branch, and it shouldn't. The original didn't. It was not a true part of the logic. And if you do it this way, where you ask if B is less than A, then you get the exact same behavior. So the mistake I made is I incorrectly translated the logic from C to Rust, and the effect was that the sort isn't stable anymore. So this property that if the elements are equal, it shouldn't take this branch, was necessary to maintain that the elements retain their original order, if possible. Okay, let's talk about some methodology mistakes. I did many, many different ones, like false randomness, bogus tests, benchmark in general is tricky, and bad distributions. I want to focus on false randomness and bad distributions. So let's take a look a bit at the beginning. My benchmarks look really, really promising. And some benchmarks, it outperformed the unstable sort by like a factor of 2. That looked good. But then as I added more stuff and changed things, okay, so let's take a quick look. At some point during development, to limit the effect that modules and precompiled standard library parts had, I copied the source code of the sort implementation from the standard library into my repository. And I put each inside a single module, so it was kind of comparable. At the same time, I did another change, but I didn't correlate it in my head back then. I didn't realize the correlation. Let's look at this other change I did, but because it was for me, I did it because I wanted to change something about how the tests work, not how the benchmarks work. I wanted to have a fixed seed for my randomness. So I put random numbers into some tests, and I wanted to make sure that I could repeat what happens if something goes wrong, right? If test fails, if it crashes or something else happens, I want to have a way to repeat it, even though it's random and unique per session, right? So I had this, I used the rand library. It's probably the most popular random number library for Rust. And I initialized this one value, this like a seed, and then I used that as my building block for all other randomness. This random vec function produces me a vec of I32, and it gets seeded with this fixed seed. And there was some time in between. I spent some weeks doing something else and whatnot, and then I came back, and suddenly the benchmark results contradicted all my microarchitectural understanding. Initially, I thought it was because I copied the source from the standard library, and now like the compiler somehow differently sees the code in a different way, and it just gives you very different results, but it just didn't really make any sense. So let's look at how these benchmarks worked. I used criterion to do the benchmark, and we see here we have a function, the sort functions get called with some test data, and it's provided by this pattern provider, which gives us different patterns, so like random, ascending, and whatnot. A bit more on this later. And we use iter batch. That's the really important part here, where we say, for each iteration, I want a new input. And then I had this like, I was writing up something, and then I was like, wait, so like, what exactly does a fixed seed mean for the rand library? Because this is what I believed it meant. So you have a fixed seed, and then it gives you, for example, we ask for 2 random numbers. We get 2 random numbers, and then I ask for 2 more random numbers, and I get 2 different random numbers, and it keeps going. But if I put in the same seed, I would get the same sequence of random numbers. So there's some internal state it tracks, and it can produce the same sequence of events, essentially. But then I did a little test, and this is actually what it means. So like, if I ask for 2 random numbers, I get 2 random numbers, but if I ask for 2 more random numbers, I get the same 2 random numbers. And the fact was that every benchmark used the same numbers again and again and again and again. And the branchy sort, so a sort with branches, which the existing sort is, compared to this like branchless sort, can outperform a branchless sort if it has perfect branch prediction. And I had spent like several weeks working on this, and then like, oof, I felt pretty stupid at that point. It was a lot of work down the drain, but okay. So that's how I fixed it. I have a new function called disable fixed seed. And if this function gets called, by default it uses a fixed seed. But if a function is called, it will then start using just random numbers as seeds. And inside the benchmark harness, I call this function at the very beginning. I call a little test function to make sure that I produce 2 random vectors. I compare them, and they should not be the same, right? To ensure that I don't make the same mistake again. So I changed multiple things at once, right? We rarely change a single character and then rerun all our tests and benchmarks and analysis and whatnot. And in my head, I incorrectly correlated these events. I thought that I changed something that only affects the tests, but it also affected the benchmarks in a very significant way. It was combined with like multiple weeks of pause and whatnot, so it wasn't as clear cut as it's shown here, but that's kind of the mistake I made, right? Wrong correlation of cause and effect. Let's talk a bit about the benchmarks themselves. I had different dimensions along which I wanted to test. I had different types. So like an I32, which is just the basic one used for many, many benchmarks. That's also the only one used by the provided benchmarks for flux sort. But I wanted to use different types because, right, it's a general purpose sort and it should work well for all kinds of different data. So a U64, a string, 1 kilobyte of stack value, 2 F64s that have a relatively complex comparison function, some patterns like random, ascending, and whatnot, many more, different sizes, and a hot and cold prediction state, but I will not talk much about this last one. It's not relevant right now. And let's take a look at the results. Maybe let me describe this graph. So as we saw, we have many, many dimensions. This gives us a huge space. So let's say we fix it down to like hot prediction state, one type, I32 at the very top, you can see this. And we want to know how much faster the new version is versus the old version. And each dot is one combination of size and pattern. That means 100 means the new one is twice as fast as the old one. And minus 100 would mean the old one is twice as fast. So it's symmetric in that way. And we can see there are about 1,000 dots along this, and also a small spider, I think. And this is what the baseline looked like. So for the random pattern, which is drawn in, it's really good. For many patterns, it's about equal. For some patterns, it's worse. For some patterns, in between. But if you compare this to U64, like very similar type, essentially, that is also small, easy to copy, there's a very curious shift. You can see a lot of points go from like not changing much. Many patterns they now look like the random pattern. And that's curious, right? Because my intuition tells me I32 and U64 should perform similar. Not identical, but similar. And that's a very, very different result. In essence, U64 performs like the random pattern across most patterns. And so I asked myself, why is that? Let's take a look how I transformed the I32 to U64. I looked at it carefully, and my idea was back then, I wanted to have values that are actually inside the U64 space. So I multiplied by itself, and multiplying a 32-bit number by a 32-bit number should be inside a 64-bit space. But if you look at it, if we just put in some numbers, the result doesn't maintain the pattern at all. Like, this is an ascending pattern, but we get random numbers. The mistake I did was, like, I turned an I32 into an I32 because I used a closure and never specified a return type. I thought I specified U64, but I didn't. So this is a better version. This is a fixed version. I'm very explicit about the kind of types I want. And then I get actually something that maintains the input pattern and works. Even one change I did more was that it now only works within the U64 space while maintaining the input pattern. Another very similar issue was that I looked at my statistics for comparisons. Like, I wanted to know how many comparisons are done for different types and sizes, and comparing it to the old one, because the comparison function is user provided, so it could be arbitrarily complex and arbitrarily expensive. And if you do way more comparisons, and this is your bottleneck, the performance for the user will be worse, even if maybe the stuff around it is faster. And this is curious, right? This tells us that for all the sizes below 20, somehow this one type does way more comparisons for the ascending pattern. And that's strange, because I know that the new implementation does the absolute minimum of comparisons if the input is already sorted. So if it has 10 elements, it will do 9 comparisons guaranteed, and that's it. And that's the same that the existing one did. It does for sizes below 20, it did an insertion sort. So how on earth does one type suddenly do more comparisons than the other? And the story is a similar one, right? The transformation I wrote that went from I32 to this like F128 type, it was wrong. I will not go into the details, they're not super important here, but just to give you an idea. Before, if we just plug in 0, 1, 2, for example, 0 gets turned into infinite. And this accidentally, by like not maintaining the input order with this ascending pattern, it hits the absolute worst case of the new implementation, and it does way more comparisons, because the very first element is not the first element, needs to be pushed to the very end. So yeah, the mistake I did was I wrote bad type transformations. I wanted to add some basic data, some random data, or some basic pattern data that all was encoded as I32s, and I tried to turn them into different types for my tests or benchmarks. And the effect I got by writing these bad transformations was I got benchmark results which are misleading and wrong. They're not useful in that sense, because they don't talk about the kind of pattern they're talking about. They talk about some other, times randoms, times kind of different. So yeah. And now I want to talk a bit about a rather subtle issue, I would say. Let me talk about the discovery, how I discovered this issue. And I have statistics that look at just how many comparisons are done in my sort. And they say that to sort slice with random elements of 10 elements on average, so I polled it 1,000 times or so and measured how many comparisons it does. On average, it does 3 comparisons. At the same time, my tests all claim that it works, that it's correct. So like across patterns, sizes, my tests pass. Let that sink in. Somehow it is both simultaneously correct, but somehow uses impossibly few comparisons. And this makes no sense. My first assumption is my tests are wrong. Somehow it can't be correct. But I look at my tests and I'm pretty sure it works correctly. And what's even weirder is like the sort statistic produce reasonable results for the existing implementation. So let's maybe just look at the sort statistics. Maybe something weird is happening there. We have a type called comp count. It has a value, again, an I32, that's actually used for the comparison, and then it has a cell, this counter. And in the comparison function, we use the comp count to increment each time this like user-provided function, which we defined here, is being called. And we do the comparison, and then at the very end, we go through the slice and sum up all the elements. It works for the existing implementation, but it didn't work for the new implementation. So I asked myself, what's the difference? And I really did some some debugging and everything. I looked really at the implementation, and I wanted to see how this works and what the effect is. And at the top, you have a function that was or is part of the existing slice sort implementation. It takes the first element and pushes it as far rightward as it needs to go to assuming that everything after the first element is already sorted. So that's the core of an insertion sort, essentially. And the other function, the new one I wrote, is very, very similar. It just takes the last element and assumes everything before it is sorted and pushes it to the left. Very, very similar. Let's look at this insert tail function that we just saw. Let's just take a look at the internals. This is just an extract, but essentially this is what's important. You have the setup for the loop where we take this last element, we read it into some temporary memory on the stack, we do a comparison. If we don't need to do anything, then we leave, and we say, okay, it's already sorted, it's good. And then afterwards this happens. And now maybe I should talk a bit about panic safety. That's something I mentioned earlier that in C doesn't need to care about this. And we have the idea that this user-provided function could panic at any time. And inside of this loop we're seeing here, it will go and duplicate elements inside of the slice. And instead of doing a swap each time with a temporary, it creates one temporary and then duplicates elements, and only at the very end it copies the element into the place it needs to go. That saves on some moves, essentially. And especially if the type is big, these moves can be expensive. And how this works is by having this insertion hole type. And it has a drop implementation which takes source and copies it into dest. So the source will get copied into the destination, and we update the pointers of insertion hole in a way that at any point where is less, this user-provided function which could panic is called. If it panics, we correctly patch up the thing we just duplicated. I'll look at it in a second to see just it going in action, to get an idea how this works. And then at the very end, if it exited normally, no panic, it uses this to patch up the hole. And if it exits with a panic, it also uses this mechanism to make sure there's no duplicate elements, because duplicate elements for a string, for example, would be disastrous. It would have the same pointer, double free it, and there's some other issues too, right? Like, you shouldn't duplicate elements once you give them back to the user. So let's take a look at what this looks like. We have a slice with elements 2, 5, 6, and 3. And then we'll run through. In the middle, you see the execution, just a line that's happening. On the left, you can see kind of like a simulation of memory. And then we're creating the pointers to it. And I'll just let it through. Now we're in the loop. We did the first comparison already. Now we're inside the loop. We set up the pointers. Then we do another comparison. We check, okay, is 3 less than 6? Yes, so we need to keep going. And then we copied it. This is what I said. Now we have 2, 5, 6, 6 in this heap allocated user-provided slice. And it should never be given out like this to the user. So we keep going. We do another comparison. And then, okay, we check. And then we update the pointers. We again duplicate the elements. This time we're taking the 5, duplicate it. And then we keep going. Another time we go to the loop. Again, we do another comparison. But this time, we found the right spot. So we leave the loop, and then we call the destructor like a drop implementation of whole. And this does this copy of source to dest that we talked about. And we can see now it's 2, 3, 5, 6. It's sorted. Looks good. Okay. What if you change the scenario very slightly? What if you say we have 2, 5, 6, 7? Just the last element changed. We have 2, 5, 6, 3, and now we have 2, 5, 6, 7. We see, okay, we create this temporary on the stack. Then we call the comparison function. We hand in as reference the stack value. Oh, it's already sorted, so we leave the function, we leave it. The hole was never created, so source never gets copied back into dest. We temp just disappears, it's a manually dropped, so nothing happens, it doesn't get dropped. And in essence, what the user now has is a slice that's sorted. It's what they provided, but it's also the bug, right? If you look at what the user observes as values, we created this temporary stack value, we use it and pass it into this comparison function that the user provided, and then we never copy it back. In other cases, where like the execution continues, as we saw earlier, it gets copied back, and then the user sees a unique version of this type. But here, essentially, the type the value diverges and like what versions are seen of it. This would be the fix. We just move this creation of this temporary stack value after this check. At the very beginning, we use the address of the heap-based slice element. So if we return here, then we're sure that it will have never seen this other version that we haven't created yet. And if we continue, we create this version, we only use this new version for comparisons. And this new version then gets copied back at the very end. And I want you to ask yourself, do you consider this a bug? Because if you look at the documentation and the contract of what the sort implementation says, I'm not sure it promises anywhere that like if you self-modify yourself inside the comparison function, you will see all effects this has on your own types. It's, as far as I can tell, it's sound. The fix is easy, right? Like this is a good idea to do this because it produces surprising results. But I'm not even sure what the name for this thing is. I called it uniqueness preservation, but probably it has a name somewhere, I just don't know it. But I found this quite subtle, and if you had just told me at the beginning, if I looked at this like 20 lines of code with like panics, like panic safety and unsafe everywhere, when I wrote this, I had all different kinds of things in mind. I was very focused on not making soundness mistakes. This was not something I had in mind. I only discovered this because I wrote this like sort statistic, and as far as I can tell, the standard library didn't have tests for this. So probably it would be caught at some point if assuming this would have landed in the standard library at some point, some user would have noticed. But it's quite a subtle issue where it's not clear what kind of behavior is expected. I would say it's expected that you can observe all changes that happen to your own types, but I don't know. I found it quite subtle, and yeah. So the mistake I made is I made a very small change when I ported insert head and made a copy insert tail that's very similar but just goes the other way. I made a very small change and had a very, very surprising effect on self-modifying types. Something I didn't anticipate, something I didn't think about at all at the time. Yeah, and with that, we come to our conclusion. It's perfectly normal and okay to make mistakes. Like from beginners to experts, everyone does mistakes. And this is something where, like, for me, it's very important how you deal with these mistakes, what you do against them, but it should be a reality that we all do mistakes, right? We work on complex problems, and we are humans. We make mistakes, and that's okay. If you can, try to attempt to like find ways that prove that what your assumption is of how the world works, try to prove that it's wrong. This is an idea that comes from science, essentially. Like, come up with ideas and ways to test that what you believe is true is false. And if you run out of ways to prove that you're wrong, maybe you're right. And don't be afraid to go back and revalidate assumptions, because things change. Sometimes, even if you're the only person working on a project. And as we saw earlier with this randomness, I didn't realize the correlation of my change. So something changed, my assumptions that I had at the beginning broke, but I didn't realize something had changed. But I saw indications that what I saw didn't make sense. So I went back and revalidated my assumption. And that I put random numbers into my sort, and I have random numbers, but they're not really random. They're all the numbers all the time again, the same numbers. So even if you don't have a strong indication that something is wrong, it's not a bad idea to go back from time to time and test that what you believe is true is still true, right? About your system, about what you're building or whatever. And here are some links. At the very beginning, this is where I did all this like research in. It's still work in progress. The second link is my repository for my presentations. You can find all the sources there. And the last one is a pull request for this like improved stable sort. It's still work in progress, so there's like one outstanding issue. I'm working on it. I just didn't have a lot of time recently. But yeah, that's about it. I want to say thank you for attending my talk.